And again, good morning. I've said that every single time we've done one of these films, so I say it again. Good morning. We're coming down to the end of our semester. It's been a good one. We've been talking about analysis of variance. I'd like to spend a little bit of time on advanced ANOVAs. This is not in your textbook, and this is not stuff typically taught in an intro stat course, and I'm going to speak in a real general sense because I think this is what you need to know, okay? Before we get started on this, though, I'd like to back up a little bit, or at least, what we've been focusing on the last, few class sessions has been this one-way ANOVA. And, we have gotten real familiar with this statistical design. We remember that we have one factor, one dependent variable. We said, a typical design might look like this. This happens to be a three-group one-way ANOVA design, one factor A with three levels. We said that if this was an experiment, this factor A is not only the grouping variable, but it's also the independent variable. So in the experimental sense, this one-way ANOVA has one independent variable, one dependent variable. If we back up a little bit to that two independent sample t-test, that design kind of looked like this, didn't it? Two independent groups. And in that sense, we could say that, yeah, we have this grouping variable, which we call a factor, and one dependent variable. The numbers in these groupings are one dependent variable. Also, if this was an experiment, this group 1 would be the control group. And this factor A, again, would be the independent variable. So really the only difference between this design and this design is that in this design, we have three or more independent groups. In this design, we have two independent groups. If we back up a little bit further to that correlated t-test, we remember, we had the pre-test and the post-test with the treatment in the middle, looking for significant difference between the means of the pre and the post-test. In that sense, one independent variable, one dependent variable. So one IV, one DV. So in the experimental sense, in each one of these designs, we have one independent variable, one dependent variable. Let's talk about some advanced ANOVAs. We have this ANOVA that's actually very prevalent in the scientific literature. Open up any scientific journal and you see this. It's called a two-way ANOVA. Also called the Factorial Anova. Factorial ANOVA, but it's spelled F-A-C-T-O-R-I-A-L, but it's pronounced factorial. Don't ask me why. In the two-way ANOVA, we have two factors, A and B, one dependent variable. We have two factors, one independent variable. So a typical factorial design might look like this. And in a lot of cases, it's presented in block form because it's kind of easy to visualize. This is a two-dimensional analysis, A dimension and B dimension. we have factor A and B. In this particular design, this particular example of the factorial ANOVA, we have 3 levels of factor A and 2 levels of factor B. 3 levels of factor A, 2 levels of factor B. This particular design, in this particular example, is called a 3x2 factorial ANOVA. So in a scientific journal, you would see it called this, and it's a 3x2 because we have 3 levels of factor A, 2 levels of factor B. With the dependent variable, of course, the numbers in these boxes are our one dependent variable. Let's suppose we're perusing the scientific journals, and we're a nursing student. We're getting our BSN here at Indian River. And we're in the Journal of Nursing. We have a 300 level, 400 level nursing course, which requires a lot of work in the journals looking at the research and such. We come across this article that is entitled The Effects. Oh, the effects. What is it? It's an experiment, right? Yep. The effects of different fruit juices on blood sugar levels across gender. This is an article in the Journal of Nursing we just discovered. The effects of different fruit juices on blood sugar levels across gender. Our dependent variable, what we're actually measuring, blood sugar levels. Factor A in this case is the type of juice treatments. You see, group 1 is what kind of group? Yeah, it's a control group. So group 1 is a control group. They're just going to get regular water. Group number 2 is going to get orange juice. Group number 3, grape juice. Factor A, what's happening along the factor, the A dimension, are the treatments. So we're going to call factor A the type of juice treatments. Factor B, gender. How many genders are there? 2. Last time I looked. Male and female. The effects of different fruit juices on blood sugar levels across gender. This is a study on gender differences. There's lots of studies on gender differences. People are always interested in the differences between men and women. John Gray wrote a book on it. Men are from Venus, women are from Mars. You know, there definitely are differences. Okay, and scientists like to look for all kinds of differences. You know, in a scientific way, observe, measure, and analyze data. Right. So in this particular 3x2 factorial, we end up with a set of marginal means across the A dimension. We call these marginal means because they're in the margins, a set of marginal means across the A dimension, and a set of marginal means along the B dimension. A dimension, B dimension. One of the characteristics of this factorial ANOVA, we compute 3F statistics. Now in some intro stat courses, we actually hand compute this. And you get 3 Fs. What does that mean? A lot of partitioning. If you thought that computation for the one-way was a little bit lengthy, you should try the two-way. You know, to compute 3 F statistics, there's a lot of, it's a lot of busy work, okay? What I want you to know, we have 3 Fs. So in that ANOVA table where we just have 1 F for the one-way, we have 3 Fs. A lot of partitioning. We're not going to compute it. But I do want you to know that the first F statistic that we obtain, we call the A main effect. The A main effect F. In this case, if we detect a significant A main effect, it's telling us that we have a statistically significant difference across these treatments on blood sugar levels. Actually very similar to what we would have in a one-way ANOVA. The one-way ANOVA is just a one-way, it's a one-dimensional analysis across that A factor. So if we have a significant A main effect, it's telling us, yeah, we have significant difference on blood sugar levels across these treatments. We would do a post hoc analysis to determine where specifically the significant differences are, blah, 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 blah. Our second F statistic we call the B main effect. Or the B main effect F. The A main effect F, the B main effect F. If we have a significant B main effect F, it's telling us that we have a significant gender difference on blood sugar levels. 2 groups, male and female. So this is a little 2-group situation. So if we have a significant B main effect, yep, there's a significant difference on blood sugar levels across gender. Actually similar to what we'd have in a 2-independent sample t-test. Our third F statistic is actually what the scientists are really looking for. Scientists are in the business of doing a lot of things, one of which is we like to look for the relationship between variables. And so the third F statistic is called the interaction effect. The interaction effect F, sometimes called the A times B effect. They're actually wondering if these fruit juice treatments interact with gender. If factor A combines with factor B in some way to produce overall differences in the dependent variable. Do A and B combine to produce some sort of effect? I don't know. What I do know is that if we have a significant interaction effect, F, we have a next step. What is the next step whenever we have a significant F statistic? Post hoc test. In this particular case, the post hocs are pretty sophisticated. A lot of multiple group comparisons, looking for, 1 and 2, 1 and 3, 1 blah, 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 looking for significant difference, where specifically is the significant difference? This is what the scientists are really looking for. Now again, this is a real general presentation, but you're college students, so what could I ask you, on the exam? Remember, as college students, you should always be predicting exam questions. What's this guy going to ask me? Well, the answers are right there. In the Factorial Anova, that means that you know that it's the two-way ANOVA. In the Factorial ANOVA, how many F statistics are there? Well, 3. Okay, it's pretty. I will ask you pretty simple questions. I'm not going to stump you on these advanced ANOVA, but I want you to know the general characteristics in terms of what's going on. What's another name for the two-way ANOVA? The Factorial ANOVA. Okay, some pretty simple questions. We have another advanced ANOVA that's very widely used in the scientific, in scientific analysis. It's called a multivariate analysis of variance. The multivariate ANOVA, also called Manova. Manova. The Manova. You see a lot of them. The multivariate analysis of variance. The literature's chock full of it. It's a really interesting, kind of cool type of ANOVA that uses one factor, two or more dependent variables. One factor, two or more dependent variables. A typical Manova design might look like this. In this particular case, we have one factor A with 3 levels. Oh gosh, this looks kind of familiar, doesn't it? Yeah. Somebody's phone goes off. Great. One factor, 2 or more dependent variables. Let's suppose we're back in this, we're a senior getting our bachelor's degree, and we have a class that requires some research, and we have to really get into the journals. We're in actually the College of Education, and we're looking at the Journal of Educational Research, okay? And we find this article, and it has this title. The effects, what does this tell us? It's an experiment, right? The effects of different instructional methods on math, reading, and spelling scores. The effects of different instructional methods on math, reading, and spelling scores. Oh, we have 3 dependent measures. We're going to call D1 math, D2 reading, D3 spelling. 3 dependent measures. Manova design. This first group, in an experiment, the first group is always a control group, isn't it? Yeah. First group is a control group. These particular students get a traditional instructional method, traditional instruction. Group 2 gets method number 1. Group 3 gets method number 2. This is an experiment. Traditional instruction. Method number 1 is some new, very innovative, creative instructional methodology using media and other, things. Method number 2 is something very similar to method number 1. The design would look like this. Three dependent measures under each treatment. So we see that this is kind of an expansion of what we're doing in the one-way ANOVA with more dependent variables. So we would have, in this case, 9 sets of scores. And 9 means. Nine sets of scores and 9 means. Class, I have a question for you. I know you're going to get it right. If we have a significant omnibus Manova F, It's telling us we have overall significance across all these means. What's the next step? Post hoc test. That omnibus Manova F is just a general indicator of significance. But it's not telling us specifically where the significant differences are. So let's write in our notes, if we detect a significant omnibus or overall Manova F we proceed to post hoc, don't we? Yeah. We proceed to post hocs. Except these post hocs are a bit more sophisticated. They're not that complicated, but they're just more sophisticated. These particular post hocs we call a step-down analysis. This is called a step-down analysis. And the first piece of this step-down analysis class is to conduct a little series of one-way ANOVAs. We would conduct a little series of one-way ANOVAs on each dependent measure. A little series of regular one-way ANOVAs on each dependent measure. And we would treat these one-way ANOVAs just like we always would treat any one-way ANOVA. So let's do a little quiz work here. Because you guys are familiar with one-way ANOVAs, right? And the characteristics of them? Of course. You guys are good students. Okay, here we go. I've detected a significant omnibus Manova F, so I now proceed to post hoc examination in the form of a step-down analysis whereby I do a series of one-way ANOVAs on each dependent measure. Let's start with D1, which is math. If I detect, on this little one-way ANOVA here, if I have a significant omnibus F, what's my next step? Post hoc test in the form of Tukey or Chaffee or Dunne or Bonferroni. I treat these just like I would any other one-way ANOVA. Okay, let's try this again. The one-way ANOVA on D2, which is reading. If I have a non-significant F statistic here, what's my next step? Stop. If I have a significant omnibus Manova F on D3, what's my next step? In the form of Tukey, Chaffee, Dunne, or Bonferroni. Good, good. So we treat these one-way ANOVAs just like any others. So step 2 will either be, post hoc, in the form of Tukey, Chaffee, so on and so forth, or what? Stop. So we treat these just like any other one-way ANOVA. Again, all we're doing is getting way more specific as to where the significant differences are. Multivariate analysis of variance. Now again, you as students should be predicting test questions. The questions on this will be very simple. In the Manova, how many factors are there? 1. Real simple questions. I don't want you to sweat this. The reason I'm introducing this is because I just want you, I think it's important. My job is to impart knowledge to you. These analyses are very prevalent, okay? This is the stuff that we learn in advanced statistics classes. Okay, I had a whole semester just on ANOVAs. Imagine that. Whole semester just on ANOVAs. You guys remember that repeated measures design? Oh yeah, how could you forget? Remember the repeated measures design? You know, we had the pretest. Oh yeah, here we go. We had, you know, that one group of subjects and the post-test. Yeah, and we had that treatment in the middle, and we had those scores. Remember, we were looking for significant difference between the mean of the pretest and the mean of the post-test. And we had that analysis called the correlated T. Remember that? Yep. Well, guess what? Similar to the one-way ANOVA, whereby, you know, the one-way ANOVA is actually an extension of the two independent sample t-test. We have an extension of the correlated t-test. Remember when I said there's a whole family of these repeated measures designs? Yeah. Let's talk about one of them. It's a very popular analysis. It's called a repeated measures ANOVA. The repeated measures ANOVA. Very, very widely used ANOVA in the literature. If we treat this pretest as the first measurement, let's call this time 1. We'll call it, it's the first measurement. Let's call it time 1. Post-test time 2. We can create more time measurements. How about time 3? Time 4? Time 5? And so on. We can actually measure our subjects as many times as we want. And of course, we can have as many subjects as we want. And these databases typically get really, 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 really large. But we have, you know, measurements. This stuff is used a lot for tracking, you know. Subject number 4, Tom Smith. I wonder how he's doing over time. These time measurement intervals can be spaced however we want to space them. You know, once a month, once every 6 months, once every 2 weeks, or we could even vary those. You know, we could have a treatment here, but maybe skip a treatment and put a treatment here. And look for significant difference, you know, across T4, T5. We can do whatever we want with this particular design. But again, one group of subjects measured many times. So guess what? We have many means. And I can 3, 4, 5, yep. As many means as we have time measurements. If we have a significant omnibus F in this repeated measures design, what's the next step? There we go. It's going to tell us more specifically where the significant differences are. So we have this extension, you know, of the correlated t-test, which is within the family of, you know, repeated measures designs. It's called the repeated measures ANOVA. Very widely used analysis in the grand scheme of scientific research. You see this everywhere. And all you got to do is, of course, Google it. Yes?
I have a question.
Yes?
Anything past your control group, which is the pre, are those all post?
The pre is not the control group. The pre is actually the first. Yeah. So this would be, you know, the time 1, time 2 mean, time 3 mean, and so on. We're actually, the subjects serve as their own controls. So this is not technically a control group, but we are controlling for the individual differences among subjects. So what was your question?
So you still have a pre and then the rest are the post?
You could think of it that way, yeah.
Okay.
Yeah.
What if you throw in another treatment, then what is it?
It's just the same thing. You can have as many treatments as you want. You can do whatever you want with this thing. I just happened to put one right there just because I felt like it. You know, you could have, you know, 20 time measurements and put treatments along there wherever you want, just to see if we have a significant difference.
Okay, just see if there's a difference.
Yeah, that's all we're, significant difference. We have another very widely used ANOVA called analysis of covariance. Analysis of covariance, commonly referred to as ANCOVA. Analysis of covariance. This is a special type of ANOVA that can come in the one-way version, in the two-way version, in the Manova version, in the repeated measures version. A lot of different varieties of this design. This is very widely used. It's all over the scientific literature in all scientific disciplines. It's considered a hybrid. It's a special kind of ANOVA. It's called a hybrid ANOVA. So it's an ANOVA, but it's a hybrid. And we know what hybrid means from genetics, right? It's been modified a little bit. And it's called a hybrid ANOVA because it uses a covariate. New term here, but not really. This covariate is a potential confounding variable. It's a potential confound. We know what a confounding variable is. We had it, I think, the first day of class. It's right back in, that confounding variable is some other variable, remember? Associated with the independent variable and the dependent variable. It may be affecting the accuracy of our results. Bless you. Is it the treatment that's causing the change in the dependent variable, or is it some other factor associated with the treatment or the DV that's causing the change? This is always a question. Now, the cool part about this particular analysis is that the effects of the covariate are factored out. And I will give you a detailed example in a minute. The effects of the covariate are factored out, thus producing a more refined or perhaps accurate F statistic. The effects of the covariate are factored out, thus producing a more refined or accurate F statistic. What do we mean by that? Well, I'd like to kind of revisit this example that we actually presented and discussed the first or second day of class. I think it was the first day of class when I was talking about the confounding variable. And all you really have to do is just go right to the beginning of your notes to that little section. And I think I discussed a study in the Journal of, I think it was the Journal of Reading, that actually has a title, The Effects, oh, there's an experiment again, the effects of different instructional methods on reading achievement. In, let's just say, Port St. Lucie sixth graders. The effects of different instructional methods on reading achievement in Port St. Lucie sixth graders. And I believe I drew the design that first day of class kind of like this. You didn't know it was a one-way ANOVA. Now you do. We had one factor A, of course, with 3 levels. And I think I drew it as group, group 1 is always a control group. They get traditional reading instruction. Group number 2 gets method number 1. Group number 3 gets method number 2. And these 2 experimental groups, again, are very innovative, just kind of like modern, teaching techniques using media and this, that, and the other thing. The dependent variable, of course, was reading achievement. Independent variable, type of instructional method. And I think we had 100 subjects in each group. Am I correct?
Yes.
Yeah, 100 subjects in each group. And I believe the mean of the first group was 75. The mean of the second group, 76, or something like that. The mean of the third group, 96. And we look at this data, and we immediately say, wow, look at method number 2. Look at that high reading mean. But I remember I forgot to tell you that when I went into Port St. Lucie Middle School to do this study, I didn't use randomization. I took the easy way out. These subjects are volunteers. I actually walked into Mrs. Jones's class, measured them. Mrs. Thomas's class was using method 1. I measured them. And then Mrs. Smith's class, using method 2, I measured them. But Mrs. Smith's class, these are the gifted students. All these kids' IQs are above 145. These kids are all high IQ. IQ is highly correlated with reading achievement. We have a confound here. We're going to call it a covariate. It's a confound. It's IQ. So now the question becomes, is it method number 2 that's causing this relatively high reading achievement score, or is it just the fact that IQ and reading achievement are highly related? What's actually causing this? Okay. The way it stands now, if we were to run a generic one-way ANOVA on this set of data, we would have a significant F statistic because of the between-group variation associated with this really high mean. MSB would be substantially larger than MSW. F would be rather large. We would reject the null, wouldn't we? Yeah, and we would conclude, yeah, we have a significant difference across groups. Now we have to run post hoc tests to determine where specifically the significant differences are, blah, 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 right? If we were to run, however, an analysis of covariance whereby we factor out the effects of IQ on reading achievement, and F is still significant, we can now conclude that, yeah, it was method number 2 that's causing this, because we've now factored out the effects of IQ on reading achievement, and yeah, we still have a significant difference. Yeah, we rejected the null, yeah, in the ANCOVA. But if I run an analysis of covariance, right, thus, factoring out the effects of IQ on reading achievement, and F is non-significant, thereby accepting this statement, if I run the ANCOVA and F is non-significant, and we would accept the null, right, I can now say, you know what, you guys, after factoring out the effects of IQ on reading achievement, there's no difference. It's the IQ that's causing this relatively high reading achievement score, not the method number 2. Now, this design is very widely used, and you see its value. These covariates typically are established historically in the literature, Like for instance, socioeconomic status is related to a lot of things. Like, you know, in health research, typically higher SES groups are overall healthier than lower SES groups for a lot of reasons, right? So what they do is they identify SES as the covariate, factor out the effects of SES on whatever they're looking at, right? It gives them a clearer picture as to what's going on. Now what we just focused on here was the one-way ANCOVA. It's a special form of one-way ANOVA. Identifying a covariate, factoring out the effects of the covariate, gives us a clear picture as to what's going on. We have factorial ANCOVAs. We have multivariate analyses of covariance. We have repeated measures ANCOVAs. What makes them all similar is that they all establish some covariate, factor out the effects of the covariate on whatever they're looking for, gives them a clearer picture as to what's going on. So you see a lot of these special types of ANOVAs called ANCOVAs in the scientific literature. Now again, keep it simple. You you learn about this in advanced statistics classes, and a lot of this stuff's taught in graduate school. So if you take stats courses in grad school, you will have this. I actually teach this in detail to my doctoral students. But again, it's the best way to start out studying anything is to start out in its simplest form, and this is exactly what we're doing. So I'm just going to ask you some real simple questions. By no means don't freak out over any of this. Okay, the advanced ANOVAs. I would like to now start into our section on, this is actually our last section of our course. And we call this analysis of categorical data. Analysis of categorical data. Now there are many of these analyses of categorical data. Chapter 11 in our textbook covers the two simplest ones. And we call these analyses chi-square. Now we call this chi-square or chi-squared. It's chi-square or chi-squared. And it's a Greek chi squared. This is not an x, it's a chi. This is another hypothesis test. It's a hypothesis test that examines the frequencies of categorical data. It examines the frequencies of categorical data. So we're going to now be working at the level of frequencies or counts. Before, when we were working in ANOVAs, we were working typically with continuous data, ratio data, true 0 point inches, meters, height, weight, feet, stuff like that, stuff with true 0 points, stuff like that. Now we're going to be dealing with counts, these frequencies. This particular analysis determines whether the observed frequencies new term here, we'll talk about it. It determines whether the observed frequencies equal hypothesized expected frequencies. It determines whether the observed frequencies equal hypothesized expected frequencies. What do I mean? Well, we have a couple of new terms here. Always have new terminology. Remember, this stuff is a language. Okay? The observed frequencies are kind of a no-brainer. These are the frequencies we see. The frequencies we see. I see 30 students in this class. I see 14 females and 16 males. These are the observed frequencies, the frequencies we see. Let's suppose I asked 300 individuals, what's your favorite M&M? What's your favorite color M&M? Well, as it turns out, after doing this, I ended up with 3 categories: green, red, and blue. 50 people told me that they prefer the green ones. 100 told me that they like the red ones. 150 said, no, my favorite M&M's the blue. These are the observed frequencies. And I'm going to put a little O there. This means observed frequencies. And if we add these numbers up, we get 300. These are the frequencies we see. The expected frequencies are a little bit more challenging to understand. Let's keep this thing simple. The expected frequencies are the frequencies we'd expect by chance. The frequencies we would expect by chance. What do I mean by that? Well, you know what? To be perfectly honest with you guys, I don't eat a whole lot of candy, and I don't really know a whole lot about candy or M&Ms or whatever. You know, for all I know, the preferences for M&Ms would be equal. Beats the heck out of me. These are the expected frequencies. The frequencies we would expect by chance. Another way of interpreting this, and if you actually Google, remember I suggest you Google all these statistical terms. There's tons of information on all of these. If you Google expected frequencies and you look at the Wikipedia, it will tell you the expected frequencies are the frequencies we'd expect under a true null. The frequencies we would expect under a true null. Think about the null. Think about the characteristics of the null. What mathematical symbol is always in that null? The equal sign. Yeah. What do we have here? Equality. We have a null hypothesis in the chi-square, which states that the observed frequencies equal the expected frequencies. Now, we are out of the world of mu. We're not dealing with population mean anymore. We're dealing with population frequencies. The observed frequencies equal the expected frequencies. F sub 0 equals F sub E. Yes, sir?
So would that kind of like always make basically the sample size divided by the number of...
Exactly. 300 divided by 3 equals 100. Yep.
So that would always be what the expected frequency?
Yes. For the one way. For the one way. The stuff we're doing today. Yeah. We know the null implies no difference, don't we? In this case, no difference between O and E. The alternative is the opposite of the null. The observed frequencies don't equal the expected frequencies, aka there is a difference. The research question here is, do a significant amount of individuals prefer blue M&Ms? Is there a significant difference across categories? Our first chi-square statistic, and again it's presented in chapter 11. is called the one-way chi-square. The one-way chi-square. Also called the goodness of fit test. The goodness of fit chi-square. The one-way chi-square, which we're actually working on now, examines for significant differences. There's that term again, significant difference. What are we doing? Hypothesis testing. We're trying to reject a null. Same drill, different research question. Different type of data, categorical data. This analysis examines for significant difference. Between categories along one dimension. It examines for significant differences between categories along one dimension. Along one dimension. In this case, green, blue, red. We call this a unidimensional analysis. Unidimensional, we know a one-dimensional analysis. The one-way chi-square. You know, in this particular example with the M&Ms, is there a significant difference on M&M preference across green, red, and blue categories? I don't know. What I do know, we can set alpha equal to 0.05. We know that before we run any statistical test, P and alpha are identical. It always changes. Degrees of freedom in this case is the number of categories minus 1. The number of categories minus 1. 3 categories minus 1 is 2. We can find a critical value. We go to the back of our textbooks to page C23. Very quickly, go to the back of your textbooks to page C23. On page C23, we have a table of chi-square critical values. In the upper right-hand corner, you see the chi-square sampling distribution, which is a one-tailed sampling distribution. If you notice, there are no negative chi-squares. Very similar to what we're doing with F, but it's not F, it's chi-square. We're working at the level of the category, counts. We go across the top to 0.5, down the side to 2df, and there's a number there. What is that number? 5.991. If chi-square exceeds this, we have enough evidence to reject the null. Chapter 11, of course, will tell you the chi-square formulaically sum O minus E squared over E. Sum O minus E squared over E. This is a very simple computation. Nothing like the one-way ANOVA or anything. Very, very simple. Will be done in a minute. Let's see how this works. O minus E squared over E. We'll start with green. 50 minus 100 squared over 100 plus red, right? 100 minus 100 squared over 100 plus blue. 150 minus 100 squared over 100. Sum O minus E squared over E. And we just bring this along. 50 minus 100 is negative 50 squared is 2,500. Divided by 100 is 25. Second category, 100 minus 100 is 0. Squared is 0 in the numerator, we have 0. Plus third category, 150 minus 100 is 50 squared, 2,500. Divided by 100 is 25. Our chi-square, in this case, is 50. We have a decision to make. Using the rule, we compare the calculated statistic to the critical value. We see it exceeds it. Therefore, our decision, obviously, is to reject the null. Yeah. We know that the p region got smaller as the result of the needle shift. What we have here is a pretty rare event. Rare events are significant events. A rare event in your life, getting married, doesn't happen every day. It's a significant event. Yeah. Something's going on here that's pretty extraordinary. We now have enough fuel, we now have enough ammo to answer our question. So let's answer it. Class, do a significant amount of individuals prefer blue M&Ms?
Yes.
Yeah. Yeah. We actually accepted the alternative hypothesis, which states that there's a difference. The observed frequencies don't equal the expected. They actually equal the observed. Now there is, again, a small chance that my decision to reject this null was not a correct one. So there's pretty high likelihood that my decision was a correct one. And the likelihood I committed a type 2 error, of course, is a non-issue. The one-way chi-square. Looking for significant difference unidimensionally. Is there a significant difference across categories? Let's try this again. Let's suppose, well, I tell you, I have a question for you. What's your favorite vegetable? Think. What is your favorite vegetable? Well, as it turns out, we asked 200 individuals, what's your favorite veggie? We ended up with 4 categories. Broccoli, carrots, green beans, and Brussels sprouts. Brussels sprouts, little cabbages. They can be kind of bitter. 4 categories. Well, as it turns out, 55 people said they prefer broccoli, 45 carrots, 62 green beans, 38 Brussels sprouts. We have our observed frequencies. I'm wondering if we have a significant difference across categories. Do a significant amount of individuals prefer green beans and broccoli? I don't know. It all depends on where that chi-square falls on that chi-square sampling distribution. 200 divided by 4 is 50. Our expected frequencies are 50. The frequencies that we would simply expect just by chance, or the frequencies we would expect under a true null. And again, we see, statistical equality, so to speak. We're going to set alpha at 0.5 again. Degrees of freedom is the number of categories minus 1. 4 minus 1 is 3. We can find a critical value We go across the top to 0.5, down the side to 3. And there's a number there. What is it?
7.815.
7.815. If chi-square exceeds this, we have enough evidence to reject the null. We can compute this chi-square. Same drill. In the chi-square, again, sum O minus E squared over E. And we do this, 4 times, 4 categories. Broccoli, sum O minus E squared over E. 55 minus 50 squared over 50 plus carrots, 45 minus 50 quantity squared over 50 plus green beans, 62 minus 50 quantity squared over 50 plus Brussels sprouts, 38 minus 50 squared over 50. A lot of arithmetic here. A lot of busy work. I took care of that for you. If we compute these operations and then square each numerator and divide by 50, we end up with 338 over 50. Or a chi-square calculated value equal to 6.76. We have a decision to make. Again, we compare the calculated statistic to the critical value. We see it doesn't exceed it. Therefore, our decision based on this null is to accept the null. We know the p region got larger because the needle shifted from the critical value back to 6.76, actually made the p region larger than alpha. We now have enough information to answer our question. Class, is there a significant difference across categories on veggie preference? No. What we're probably seeing here, just happened by chance. We really don't have a significant event here. Actually a pretty common event. Nothing really extraordinary is going on. What's probably happening in the population is that the observed frequencies actually equal the expected frequencies. No difference on veggie preference. Probably what we're seeing here just occurred by chance. Now again, we know alpha is kind of a non-issue, but whenever we accept the null, there's a small chance that we may have committed a type 2 error. Yeah, same stuff. Same, different statistical tool designed to answer another research question. Let's very quickly try this one more time. Class, think, what is your favorite automobile? What is your favorite automobile? Well, I tell you what, let's get a little more specific. In terms of reliability, do you think Japanese cars are more reliable than American cars?
Yes.
What you just did was put forth a hypothesis. You believe that categorically, Japanese cars are more reliable than American cars. Let's test this hypothesis with some research subjects. We already did this. We sampled 370 subjects. And we asked the question, what's your favorite automobile? We ended up with 6 categories. Honda, Toyota, Nissan, Chevy, Dodge, Ford. 6 categories. Looks like 3 Japanese, 3 American. Turns out 84 individuals said that they like Honda's the best. 79 Toyota, 75 Nissan, 49 Chevy, 36 Dodge, 47 Ford. These are our observed frequencies, and if we sum these numbers, we get 370. Yeah. Do we see a little pattern here? Our expected frequencies, the frequencies that we would simply expect by chance, we get by dividing 370 by 6. We get 61.7 as our expected frequencies. Do a significant amount of individuals prefer Japanese cars? I don't know. Let's get this thing set up. And again, we have a null that states there's no difference, an alternative that states that there is a difference. We'll keep alpha at 0.5. We know P is 0.5. DF is the number of categories minus 1. 6 minus 1 is 5. We can find a critical value. We go across the top to 0.5, down the side to 5. There's a number there. What is it?
11.070.
11.070. If chi-square exceeds this, we have enough evidence to reject the null. We know that this is telling us that at 5 degrees of freedom, about 5% of the area under this particular chi-square sampling distribution at 5df falls to the right of this number. About 95% falls to the left of this number. Let's compute the chi-square, make the decision. Sum O minus E squared over E. A lot of work to do here. A lot of busy work. Let's do it. Honda. O minus E squared over E. 84 minus 61.7 squared over 61.7 plus Toyota. 79 minus 61.7 squared over 61.7 plus Nissan. 75 minus 61.7 squared over 61.7 plus Chevy. 49 minus 61.7 squared over 61.7 plus Dodge. 36 minus 61.7 squared over 61.7 plus Ford. 47 minus 61.7 squared over 61.7. A lot of arithmetic. It's just the way it is. If we do all this arithmetic, if we perform all these little operations, square the numerator and divide by 61.7, we get the ratio 2011.34 over 61.7. Our chi-square in this case is 32.6. Pretty rare event. We compare the calculated chi-square to the critical value, and we see that it exceeds it. Therefore, the decision would be to reject the null. Yeah. And conclude that we have a statistically significant difference across these categories on automobile preference. It appears that, you know, a significant amount of individuals prefer Japanese cars. However, what could be an issue here? Let me give you a hint. In terms of sampling, what could be an issue? Yeah, this could be a biased sample. This could be a sample of all Asian people. They're all, you know, people that live in Southern California. A lot of Asian people, you know. This might, you know, if this was a randomly selected sample, we could then generalize to the population. If this is biased, then these results are sample specific. We know the P region got smaller as the result of the needle shift from the critical value out to 32.6. It actually reduced this area of P to something less than 5% of the area under the chi-square sampling distribution. We rejected a null. And again, there's about a 5% chance that my decision's not a correct one, so I rejected with some pretty high certainty. Analysis of categorical data, examining frequencies. These are counts, using the one-way chi-square. Next class session, we will look at the two-way chi-square, which is in Chapter 11. We will have our next examination a week from today. So Thursday, we will finish the section, maybe have a little review. And that is all for today. Thank you so much for attending.